Hello and welcome to the Daily Space for today, Tuesday, September 15th, 2020. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. Now, the majority of today's news is going to be focused on things outside our solar system. In fact, things outside of our galaxy in most of the case. But we are going to be coming back home at the end of the show when we're going to be doing an interview with Dr. David Grinspoon to discuss, more about the amazing Venus results we covered yesterday. We're going to get more context on, the history of our thinking about life in Venus's atmosphere and, where things go from here. But before we do that, it is galactic science time. Now, growing up, I assume many of you, had to memorize the steps in the scientific method. According to our classroom teachers, science progresses by making hypotheses, designing careful experiments to test the hypotheses, and then analyzing the results and modifying the hypotheses as needed and doing new experiments. Now, I don't know if there's any field of science that actually works that way, but that is seriously not how astronomy seems to work. Starting with Aristotle, theorists have built the theories, often without actually looking at the universe, and declared that we should be able to understand our universe from, first principles, assumptions, and careful confirmation from a few observations. Now, observers, including the likes of Galileo, Tycho Brahe, and many hundred years of following observers, have then gone out, looked at the universe, and said something along the lines of, sorry, reality doesn't match your theory. And they have demanded new theories, like Kepler's equations of planetary motion. For a couple thousand years, astronomy has advanced, one or more unexpected observation at a time. This continues to be true. One of the simple assumptions about our universe that turned out to be utterly and totally wrong was that we can see with our telescopes all the sources of gravity. We can't. Back in 1933, just 4 years after Hubble discovered the universe is expanding, Fritz Zwicky discovered that galaxies and clusters don't orbit as expected. He figured there must be some invisible pull, some dark unseen matter that is out there exerting a pull on galaxies. 30 years later, Vera Rubin found the same invisible matter is affecting the motions of stars and galaxy after galaxy. By the mid-70s, astronomers were finally starting to admit, the universe is full up with invisible material of unknown type that affects everything. By the time I was in grad school at the turn of this century, theorists were working hard to model dark matter with smooth equations that describe how dark matter falls off with distance from the center of galaxies and falls off with distance from the center of galaxy cluster cores. It was initially assumed that visible matter consistently exists in consistent dark matter halos with the light and dark tracking one another. But then the observers came along, in this case the COSMOS program, and they mapped out dark matter by looking at how it bends light of background galaxies through an effect called microlensing. And it was discovered that dark matter does as it pleases and exists on its own sometimes. Since then, we've found galaxies seemingly devoid of dark matter, and basically, dark matter, it turns out, is going to dark matter where it wants. But even with this new understanding, we continued to believe that dark matter doesn't really clump up, that it is one or a family of particles that have a very small collisional cross-section that don't really interact with the electromagnetic force and are generally thought to hang out and make up 30% of the universe. Well, it's not entirely satisfying that we can't just blow something up and create a dark matter particle in a lab that we can understand. At least we thought we had a handle on where it is and how it piles up. But then observers. I love observers. I was one for a long time. But then observers came along and used the Hubble Space Telescope to look closer at the distribution of dark matter in galaxy clusters, to look closer than anyone has ever looked before. And guess what? They discovered dark matter absolutely does not have a nice, smooth distribution. In a new article in the journal Science, a research team led by Massimo Meneghetti has determined that there are dense clumps of dark matter associated with some galaxies and clusters. This was a two-step observation. The Very Large Telescope was used to confirm galaxies belong to the cluster and to measure the velocities of the stars in these individual galaxies. This is a way to determine the galaxies' masses using orbital mechanics. They also used the Hubble Space Telescope to look at how the light of distant objects was magnified and sometimes distorted and replicated by the overall gravitational pull of the cluster, and also by the individual tugs of member galaxies. That's the unexpected part. To quote the press release, to the team's surprise, in addition to the dramatic arcs and elongated features of distant galaxies produced by each cluster's gravitational lensing, the Hubble images also revealed an unexpected number of smaller scale arcs and distorted images nested near each cluster's core, where the most massive galaxies reside. The researchers believe the nested lenses are produced by the gravity of dense concentrations of matter inside the individual cluster galaxies. These dense concentrations are not part of our current models of the universe. According to Bengetti, we have done a lot of testing of the data in this study, and we are sure that this mismatch indicates that some physical ingredient is missing either from the simulations or from our understanding of the nature of dark matter. Co-author Premvada Natarajan goes on to add, there's a feature of the real universe that we are simply not capturing in our current theoretical models. This could signal a gap in our current understanding of the nature of dark matter and its properties, as these exquisite data have permitted us to probe the detailed distribution of dark matter on the smallest scales. I have no doubt that we will quickly have multiple overlapping theories to explain what's going on. For now, though, we have a delightful mystery. I, for one, look forward to seeing if these results can be replicated with studies of isolated galaxies. It would be really cool to know if these weird distributions of clumped up dark matter only exist in clusters. Here's to hoping the team is already looking. Galaxy clusters are a common target for telescopes. They are stunningly beautiful. They host a whole lot of objects in a very small region of the sky. And they, unlike star clusters, contain a myriad of different kinds of objects. As our telescopes get better and better, and as astronomers look for longer and longer periods of time, the diversity of what we see has grown. In a new paper in the astrophysical journal, Chengza Liu and collaborators have explored the population of ultra-compact dwarf galaxies and ultra-diffuse galaxies in the Virgo cluster using MegaCam on the Canada-France-Hawaii telescope. This work was done as part of the Virgo cluster survey. These small, weird systems define the known edge cases in galaxy structure, and it is unclear if their structures are due purely to interactions within the cluster or if they could initially form this way. The ultra-compact dwarf galaxies look like either large star clusters in isolation or like the cores of galaxies that have been stripped of their halos. In some cases, wispy trains of stars surround them, leading to the thinking that they may, at least in some if not all cases, be regular galaxies that lost a lot of their content. On the other extreme, the ultra-diffuse galaxies are simply confusing, as they appear to have globular clusters, which usually require galaxy condensing events to form. According to co-author Sung-Soon Lim, The diversity in their properties indicate that while no single process has given rise to all objects within the ultra-diffuse galaxy class, at least some ultra-diffuse galaxies have appearances suggesting their diffuse nature is due to tidal interactions or to the merger of low-mass galaxies. Sometimes what amazes me most about the universe, about science, is that we can explain our universe and predict things fairly well at the largest scales while not knowing all the details. Science works, at least as long as you don't look too closely at things. But the big picture, we got that. And we're working on getting science to work when you look at the details too. One of the places where people are working the hardest may be the study of type 1a supernovae. These exploding stars are defined as growing white dwarfs that hit a critical mass and explode when they can no longer support themselves against the crush of gravity from their suddenly too large mass. Since they should all explode at the same mass, and since the same mass exploding should release the same amount of energy, it's been thought that type 1a supernova should be really good standard candles. Objects we can look at and say, okay, that should be this specific luminosity, but since it appears only so bright, it must be this specific distance away. Thing is, it turns out white dwarfs can get themselves into no end of weird situations. In a new paper in the Astrophysical Journal and led by Eric Hassot, a weird type 1a supernova has been seen growing in brightness ever so slowly. And the rise and fall in brightness of certain spectral lines didn't match what is generally expected. One theory, however, did correctly predict what they were seeing. Showing theorists do sometimes get things totally right. In this case, it appears that according to Hassot, this is the first strong observational proof that a type 1a supernova can explode in a post-asymptotic giant branch or protoplanetary nebulous system, and is an important step in understanding the origins of type 1a supernova. These supernovae can be particularly troublesome because they can mix into the sample of normal supernovae used to study dark energy. This research gives us a better understanding of the possible origins of type 1a supernovae and will help us to improve future dark energy research. Put another way, it turns out type 1a supernovae can occur in systems with a white dwarf and a giant red giant star that has already started to puff off its atmosphere, becoming a planetary nebula. From these visible weird objects, from the oddly forming stars and the disastrously distorted galaxies, the invisible is traced out, allowing us to know that our universe is mostly dark matter and dark energy, and what remains to be seen in our telescopes. It's there to test our understanding, and it's weird. The universe is weird, and it is awesome, and sometimes we understand what is going on. And sometimes it turns out what is going on is something completely different from what I expected. This concludes today's news, but it does not conclude our show. Joining us in just a moment is Dr. David Grinspoon, who, unlike me, understood Venus might be capable of supporting life. And he's going to catch us up on all the research I did not follow because I, ignorantly, due to a lack of creativity, assumed Venus was the one planet in our solar system where life would not be found. All right, so stay tuned. I'm going to put the rockets up for just a moment, and then we will be joined by David. So hold on. Hello and welcome back, everyone. Joining me is my colleague who has far more creativity when it comes to looking at the universe than I do, Dr. David Grinspoon. Welcome, David. How are you doing today?
Hi there. I'm doing fine. It's been an interesting couple of days.
So, you do an amazingly diverse collection of research. And one of the things that you've looked at that I learned that you looked at over the weekend was you were one of the many people who looked at Venus and said, "Yeah, that might be capable of having life." Can you tell me about your own history with this project with this planet before we go into yesterday's discoveries?
Yeah, I have a kind of a long history with Venus because even when I was an undergraduate, I happened to get a summer research project with a professor of mine, Jim Head at Brown University, who was studying the Pioneer Venus radar maps, and we were looking
Uh-huh.
for tectonic features. And then when I was in grad school, one of my first research projects was trying to understand the history of water on Venus. So it's a planet I've been fascinated with for a long time because it's sort of like Earth, but also really different. It's like the same size and mass and density, and seems like it was maybe sort of formed similar, but boy, have they evolved in really different directions. And Venus is almost like the poster child for the place you would never look for life in terms of what we mostly know about and think about when we hear Venus, because it's so hot on the surface and so dry. And it's just like hell there. So at least there's one place we don't have to think about life, right? But but I really started thinking about the possibility of life there in the wake of the Magellan mission in the early 1990s, when we had our first radar mapper and could really see what the surface of Venus was like. And we learned it's been very geologically active, and probably is geologically active today. So there's ongoing volcanoes and just fluxes of gas and stuff from the interior into the atmosphere. And that, because of that, I started a research project with some colleagues to look at what that surface volcanic activity was doing to the clouds in the atmosphere. And one thing we discovered was that the clouds depend on that continuing surface activity. In other words, interestingly, when you look up at Venus at night and you see that bright reflective planet, you're actually seeing the result of volcanic activity on the surface, I think, because without that, the clouds would disappear. So it turns out there are these fluxes of these flows of stuff coming out of the surface, going into the atmosphere, making the clouds, reacting with sunlight, and then going back and reacting with surface minerals. So there are these active cycles of matter and energy. And Venus is, at least in the geological and meteorological sense, not a dead world. It's sort of a living world. And then that got me thinking, well, on Earth, life is really tied to the fact that we've got so much geological and chemical cycling and activity. But that can't be the case on Venus, right? Because of the deadly surface. But then I was also studying the clouds. And one thing you notice when you study the clouds is that conditions there are pretty moderate in terms of like the temperature and pressure, like the room that you're in right now and the room I'm in right now are roughly the same as the temperature and the pressure of the planet Venus. It's like room temperature. In the
Yeah,
clouds,
once you get up to like 52 kilometers up or so.
Yeah, exactly. So 50 kilometers up, it's like room temperature and room pressure, and there's all this interesting chemistry going on, and there are these stable liquid droplets. Now, so then this was also at a time when people were talking about extremophiles and life in weird places. So then, okay, so you've got energy flows, check. You've got nutrients, check, because all the life-giving elements, it turns out, are there in different forms. You've got a stable liquid environment, sort of, check. So why not? And then the big why not is because it's really strong acid. It's like battery acid. And so that's sort of like I don't know, but the more we discover weird life on Earth, including acid-loving life, it kind of pushes us in that direction of thinking, well, maybe. So I've never said like there is life on Venus. I'm sure of it, I've said, you know what, this is plausible. And as we think about environments like the subsurface of Mars, or, methane lakes on Titan, as plausible environments where we could look, I've advocated that we should keep the clouds of Venus in this sort of plausible category. And just one more, I know I'm talking about, but just to give you the one more piece of the story, there are a few weird things about the clouds of Venus that are just persistent mysteries. Like there's this ultraviolet stuff called the unknown ultraviolet absorber, which is, it's not a very imaginative name, but it says exactly what it is. And for decades, we've been trying to figure out what is this stuff that's like sucking up all the solar energy in the clouds of Venus, and it's unidentified. And so if there was some biota, some life that had figured out how to make stuff and use that energy, there'd be a lot of energy at the surface of a biosphere. And there are a few other things like that. They're just like weird things in the clouds that we haven't explained well. So to me, that like at least keeps open a little bit of crack in the wall that tells us this is off limits for life.
So I want to step through this because Venus is one of these worlds that if you are capable of remembering the early 60s, which I didn't exist yet, and I don't think you can remember the early 60s. For those who can remember, we went from prior to Mariner 2 thinking that this was a lush, tropical, rainforesty world potentially, to Mariner 2 goes by and we find out, wow, that's too hot for anything sensible. And suddenly it became a dead world. There's this amazing change in science fiction after this happened. I remember for a while, the thinking was that Venus has always been like this pretty much, that it doesn't have tectonics, and some interpretations of the Mariner data had been that there was a massive one-time essentially upheaval of the entire planet all at once. To now we're going back to thinking that 750 million years ago, this was a regular non-greenhousey world capable of supporting life, and something catastrophic happened. We're going to start to think that there's ongoing volcanism. And I'm wondering, we haven't really gotten all that much new data because while the Japanese probe is there, it doesn't have a radar on it. How has our reinterpretation from single epoch to ongoing volcanism, from always death to fine until 750 million years ago, what's triggered these changes? Start wherever you want.
Yeah, there's a few things. One was that Magellan showed us that Venus had an incredible history of volcanic activity, but it didn't really tell us when that volcanism had happened, at least not within very, except for in a very crude sense. We knew that it wasn't, that it was more recent than like totally primordial, because you can count the craters on Venus and say, well, the average surface age is maybe less than 1 billion years. So that's, it's not that ancient. It's not like the moon where it's billions of years old, or the old areas of Mars. But we didn't really know, are these volcanoes still active today? So since that time, there's been a lot of effort and several lines of evidence that have suggested that the volcanoes are still active today. Things we've seen on the surface, things we've seen in the atmosphere. So it's looking more and more like the volcanoes are still active today. But that's still, we haven't got the, the metaphor people use is the smoking gun. We haven't found the smoking gun, but we've seen, sort of the spent bullets, but we're not exactly sure. I don't want to use all these gun metaphors, but you know what I mean.
Yes.
The volcanoes have happened. They probably are still happening, but that's been sort of a gradual accumulation of data, which is partly that shift that you're talking about. But also another big thing is that, so we've had this idea that Venus started out Earth-like. Yeah. And again, we have circumstantial evidence that there was more water, but that's also a hard thing to pin down because we just haven't had that many missions, and the early history of Venus is sort of destroyed by the later history of Venus. So we think there was water early on, but then the big question is, when did Venus lose its water, assuming it had it? And that idea, as you mentioned, sort of post Mariner 2, the idea was, well, maybe it had water early on and then there was a runaway greenhouse when the sun warmed up, and then it's been like it is now for most of its history. But another big change that's helped evolve our view is that our climate models have gotten better. And a lot of this, by the way, has to do with the effort to understand future climate change on Earth. And so people have been developing these GCMs, these global circulation models, which are the tools we use to predict, our own, the climate change we're causing on Earth. But those models have gotten better and better. And now, more recently, people have been able to adapt them to Venus. So instead of these sort of cartoon climate models that are basically one-dimensional models where you say, here's the radiation coming in, here's the radiation going out, and here's what we think happened. Now people are able to do these much more sophisticated three-dimensional models of the climate on Venus, where you include the weird rotation, the slow backwards rotation of the planet, and all these subtleties that we couldn't include before because our climate models weren't good enough. And when you model the transition, the real question is how does Venus transition from a more Earth-like place to its current really dry and hot place? And when you model that with these modern GCMs, global circulation models, and you include the slow rotation and the effect of clouds and so forth, it turns out that it takes much longer to get rid of the ocean than we thought it did. In fact, billions of years longer. So there's a lot that we still don't know, and some assumptions you have to put into these models that we would like to validate with more data. But the best climate models of Venus now suggest that Venus could have kept its surface oceans for a long, long time. Now, you mentioned up to 750 million years ago. We don't really have a very good hard number for that. It's sort of maybe up, that's it. It's like greater than or equal to that time. So it can't be more recent than that because we'd see the evidence on the surface, but it might be as recent as 750 million years ago. And beyond that, there's a big zone of uncertainty. And one of the things we'd really like to nail down with more exploration, but it seems quite likely that Venus, for much of its history, had surface water oceans, which of course is very intriguing to think that this planet next door, that Earth had a near neighbor with surface oceans for billions of years, maybe for most of solar system history. And that's kind of something that we've been learning recently that hasn't fully been, that people don't know about enough as much as they should. And we have to get the word out about that.
And so we have this concept where there could have been habitable oceans up to no more recently than 750 million years ago. And here on Earth, 750 million years ago, I looked this up. There were single-celled organisms capable of acting in colonies like sponges. And so we were already fairly far along in the whole life is going to find a way thing. And so we have both the possibility of panspermia, of coevolution, all sorts of things saying that, well, if it happened here, it could have happened there. And heck, maybe we even seeded it or they seeded us, and who knows, and we'll never know. Now, that's one cool thing going into yesterday's discovery. The other is this dark splotches, the UV absorbers that you mentioned. And it was noted as long ago as the 1970s by the likes of Carl Sagan and David Morgowitz?
Hal Morowitz.
Hal Morgowitz, yes. That there's microorganisms on Earth capable of explaining what's being seen. Can you go into that, Annie?
Yeah, I mean, Sagan and Morowitz wrote this paper in, I think it was 1967 in Nature, proposing a possible habitat for microbes in the clouds of Venus. And it was a very imaginative paper. And, I think it was considered kind of fringe at that time, but they were too obviously very, they had a lot of gravitas and were able to get this published in Nature. And then people kind of forgot about that. And it didn't really go anywhere. And people, it did not become one of the places people really thought very much about life. But they pointed out, as some of the logic I was describing earlier, that there's actually a rather moderate environment in the clouds, unlike the surface, and there are energy flows and so forth. it kind of, that didn't really go anywhere. And then, I guess what I tried to do, and I wrote this book, Venus Revealed, in the late '90s, and in a way, I was kind of reviving the idea, but it was in a post-Magellan realization. I mean, when Sagan and Morowitz wrote that, we didn't know anything about the surface,
right?
And then I realized that in a way, this realization of an active surface and the sort of active cycling of matter between the surface and the clouds and the atmosphere, along with all the realizations about the extremophiles that had happened in the interim, made this a little bit more plausible than people had been thinking. So I kind of started putting it out there again. So, it's an idea that's, it's got a long history, but I wouldn't necessarily say it's been mainstreamed for much of that history.
No, it certainly has not been mainstreamed. It's an idea that when I realized it predated me and I had never heard of it, I was slightly disturbed over the weekend. But it's come back up again. There was a year ago a paper by Lee looking at the dark splotches again and bringing up this concept again of no one's been able to find another alternative, and these dark splotches keep dark splotching. I don't know how to verb that. So here we have formerly habitable dark splotches that people have been trying to explain with microscopic life since the 60s. And then came over the summer a whole series of papers looking at how you could use the natural circulation of the atmosphere of Venus to develop ideas for a life cycle with spores in the lower atmosphere where they're desiccated, rising up. And can you explain this Hadley cell moisture cycle that has started to be such the talk of the town?
Yeah, well, I mean, it's an interesting question. If you postulate, this line of reasoning we've been talking about, where you can say, okay, so overall the cloud environment is somewhat habitable, you could argue, because of the conditions and the existence of this sort of medium of cloud droplets. But then beyond that, then the next step is, but how would organisms actually live there? Like if you're a microbe in a cloud droplet, it's not enough to say that, how do you get from one droplet to another? How do you maintain a population of happy microbes in that kind of environment? And so you have to postulate a little bit more than just, they could live in the droplets. So this idea is, well, what if the microbes, or whatever they are, these Venus creatures living in clouds, go into a dormant phase where they basically just become spores, and they can, like, when the cloud particles dry out, these spores then can become the nuclei of other particles, become what we call CCN, cloud condensation nuclei. So that then, in a sense, the sort of spore state of these things, they make their own new cloud particles. Because, I mean, it's already a fact, a well-known, people that model clouds, you need cloud condensation nuclei. You need little particles to sort of be in the atmosphere, and they're often just little pieces of dust or whatever, but that's a part of the life cycle of a cloud, is that you have these little particles that nucleate larger droplets. And so what if the nuclei are little bits of life transmitting themselves to other clouds? And it just so happens that below the clouds of Venus, there is this known reservoir of very tiny particles, smaller than the particles in the cloud decks, known as the subcloud haze. We don't know that much about it, but it's been observed by a few spacecraft. And then the circulation part you mentioned, along the equator, there's this Hadley circulation. Just as on Earth, there's Hadley circulation, which means that because the bulk of most sunlight falls close to the equator, so you get more heating, and then you tend to have rising air currents along the equator, and then it settles at other latitudes. That's definitely a big part of the air circulation on Venus. And so you could imagine this population of little particles of dried out cloud life stuff below below the cloud deck being carried up in that Hadley circulation up into the clouds and sort of completing the life cycle of these putative life forms. It's a very imaginative idea, and it, you know, at least on a basic physical level and sort of logical level, it works to help explain how there could be a self-sustaining population of life forms in the clouds. It doesn't prove anything. Obviously, we need observations and a lot more before we start to really believe this can exist. But it does help us, you know, if you could not imagine an answer to that question, how could these things possibly live? That it would be harder to imagine, you know, an inhabited realm on Venus. But the fact that people have come up with an answer to that question, however schematic it is, I think moves the conversation along a little bit, and have, you know, you go, well, okay, maybe that works, or maybe it's something else works, but at least we know there's something that seems to answer this question of how that could happen.
And so this research coming out of MIT in a lot of cases was focused on the moisture cycle and how that creates the environment for life. Now, starting in the 90s, NASA and a bunch of other funding agencies dropped a lot of money into trying to define biological and technological signatures of life on other worlds, and in trying to figure out what chemicals to look for in exoplanet atmospheres, people came across the idea of phosphine. Can you explain why phosphine of all the molecules, this phosphor and 3 hydrogen molecule was landed on?
Yeah, well, in general, we're very interested in the question of what we call, you know, atmospheric biosignatures. And the reason why we're really interested in this question right now has to do less with Venus and more with exoplanets. That we've discovered there's planets around all the stars, but we don't know anything about them. And we want to build the next generation of space telescopes that can take the detailed spectra of those atmospheres and see what's there. And then the question is, well, even if we see what's there, how will we identify life? That's what we really want to know. I mean, we want to know other things, but the real thing, the most intense thing, the thing we most want to know is there life on these planets? But how could you tell? Well, so one thing that life does is alter its atmosphere. And we see that, of course, on Earth, where all this oxygen and there's methane and things here that shouldn't be here if it wasn't for life. So could we recognize the presence of life on an alien atmosphere by just molecules in the atmosphere that shouldn't be there otherwise? And so in an effort to answer that question, as you said, there's been a lot of work that's been put into looking at what molecules we ought to find in planetary atmospheres and what molecules we ought not to find there unless there's life. And there are a few molecules that life makes that are not that easily made by other processes. And one of them that's pretty famous is methane. And we found these wisps of methane on Mars, and that's exciting because methane on Earth is made by life, but it's also made by a few geological processes, and so it doesn't necessarily mean life. Well, this work concluded that one of the best biosignature gases is this gas called phosphine, which is a phosphorus with 3 hydrogens. Why? Because on Earth, all the phosphine in our atmosphere is from life, either from, you know, like decaying animals, or from or things that are made in the guts of animals, or from industrial processes, like meth labs. It turns out make phosphine, but nobody's saying there's meth labs on Venus as far as they know. But so here's a gas that's made by life that we don't know of other geological processes that make it. You do find phosphine like on Jupiter and on Jovian planets, but that's to be expected because Jupiter's a very hydrogen-rich environment, what we call a reducing environment.
Yeah.
But in a carbon dioxide rich environment like Mars or like Venus, you don't expect to find these hydrogen rich gases just sitting there in the atmosphere. So if you find them, it means there's a source. They don't last long. The other chemicals in the atmosphere eat them. They have a very short, what we say, a short chemical lifetime in the atmosphere. So if it's there, it has to have been put there recently, or it's being actively supplied. And so that, if you find that in an atmosphere that has no obvious source of that, then it's very suggestive, and you go, wait a minute, that's a biomarker, but it doesn't prove anything about life, but it does, it's like there's a light flashing on the dashboard and you have to like figure out why.
And a lot of this work has been done by Clara Sosa Silva. And in looking at this, she's basically made her career on this one molecule. And she hasn't been able to find, working in collaborations with a myriad of different people, either the geochemical processes such as we found for methane on Mars, or the photochemical processes where sunlight and the atmosphere of Mars interact, that is able to produce phosphine. Now, as is forever a topic on this show, humans don't always have the creativity to figure out all the things the universe is capable of throwing at us. So what we're seeing doesn't necessarily say there has to be life. It says there is either life or something no one has figured out yet.
That's right. That's right. Yeah. I mean, there are a few interesting possibilities. One, of course, is that there's not really phosphine. That they made an error in the interpretation of the observations, and it's a very hard observation to make.
Yes.
I'm not an observational astronomer. As far as I can tell, they did a good, careful job. But that people will be questioning this and repeating the observation and sort of scrutinizing it carefully, which they should. Yeah. But assuming that the phosphine holds up, that it's really phosphine, then either it's life, or there's some weird chemistry that we didn't understand going on Venus, which maybe isn't quite as like, astonishing to most people out there. But for someone like me who studies Venus, it would still be really cool to learn about new chemistry on Venus, and not just really cool, but essential for this project of using biosignatures on exoplanets. If we can find this gas in an atmosphere that shouldn't have it, and then it turns out it's not due to life, we need to understand that, or else how are we going to find life on an exoplanet using these atmospheric biosignatures? And it's been very interesting watching the response on Twitter and so forth, because, all these astronomers were saying, we need to look at exoplanets to find, biosignatures by finding these gases. And then we find this gas on Venus, and
they're like,
everybody's like, that can't be life. There's got to be another explanation. There's no way it can be life. And, maybe they're right, but it makes me wonder, can we really use atmospheric biosignatures that reliably on other planets if that's the automatic response? I mean, and the real answer is no matter what, we have to be cautious. But if nobody comes up with another explanation, then I'm going to be like, okay, well, yeah. So now what?
Well, one of the things, and here's where we have to acknowledge that science is done by humans who have personalities. And one of the things that gets me looking back through the history of is there, isn't there life, with the original Viking experiments done on Mars, the majority of the calm, pleasant humans were there has to be an explanation that isn't life. And it was someone who has gone on to be described as a curmudgeon who has been across all the decades saying, no, we did this right. There is life on Mars. And he's still out there doing this, which I think is why new generations are still being introduced to him as the life on Mars curmudgeon, which is somewhat unfair, but shows human bias. With the Allen Hills meteorite, I was introduced to that scientist as the person who has graduate students in bikinis in his research photos. And that creates a certain bias. Now, with this, Sarah Seeger is a very pleasant human being, and I'm wondering if that is going to influence the ability of this research to captivate people and get a kind of traction that we haven't seen in prior announcements of this could be life.
Yeah, it's an interesting question. Those are interesting comparisons. I mean, I'd say first of all, the Mars example for the Viking experiment, that curmudgeon has been a very useful curmudgeon.
Yes.
He does have that reputation, but I think there's also kind of a grudging respect because we don't want to be wrong. And he's not a crackpot.
No.
And we want to make sure, did we find life with Viking? Maybe it was just not what we were expecting. So the weight of opinion is definitely, we did not find life with Viking, but it's good to have somebody advocating that position. Yes. And have to answer those objections. It provides a service. And then the Martian Meteorite, the image you just described is very disturbing. So, that's like, whoa. But that discovery, and yeah, I mean, I think, the larger point, it maybe wasn't socialized in the, it announced and socialized in the ideal way by the ideal people. But you can argue that announcement was very useful, even if it turned out to not be evidence of microfossils in a Martian meteorite, because it got everybody to say, well, why not? Why couldn't we find a rock from Mars that had ancient fossils in it? And it got everybody to take another look at the idea of ancient life on Mars and realize, well, it's not outlandish. And it really helped to get astrobiology going.
Yeah.
And one could imagine that this discovery, this announcement on Venus, even if it turns out to not be real, the phosphine goes away because there's something wrong with the observation, or there comes to be a generally accepted non-biological explanation. Either of those is quite likely, quite possible. But there still will have been this moment where people look at it and have to go, well, why not? What's so outlandish about life in a cloud environment? And that's what I'm enjoying this moment now, not because I necessarily expect that the end result of all this scrutiny is going to be popping the champagne corks for life on Venus. But I think it does force everybody to look at this question and go, well, how do we really know that there could not be life there? And, it's sort of, we have to look at it. It shines a light on that possibility. And that's a good thing. Even if the phosphine goes away, maybe we'll be left with a greater appreciation of the range of possibilities of life on a planet like that.
And the thing that this brings back to my mind, to go back to today's earlier news, is Fritz Zwicky, who is another difficult personality. He discovered dark matter along with Oort. We always leave Oort out of the story because he talked about globular clusters. But back in the 30s, he was already starting to advocate for dark matter. And it wasn't until after his death in the 70s that people generally grudgingly admitted dark matter is part of our universe. And Oort, Zwicky, and Rubin all largely went through most of their careers doing research on something most people said isn't real. And so you have to wonder with this research, how many generations is it going to take before people grudgingly say, yeah, there's pretty much life everywhere, or wow, we were wrong. And we don't know
I mean,
which.
there are a lot of examples. You gave a couple good ones of people that, advocated their whole life for something and in some cases didn't live to see their vindication. Another one is Melantin Milankovitch, who was the guy that came up with our accepted theory now for climate cycles and how they're driven over the long run by the gravitational influence of other planets. He was regarded as a crackpot and went to his grave without that vindication. And now we call them Milankovitch cycles after him. And there are loads of examples. Maybe after I'm long gone, they'll talk about those Grinspoon life forms on Venus. You know, you got to be careful, because just because they all laughed at what's the line, they all laughed at Edison and Einstein, doesn't mean that if they're laughing at you, you're a genius. You could just be laughable. So
it's
time will tell, I suppose.
it's so hard sometimes to be a scientist watching all of this changing in the moment. And I know one of my first thoughts yesterday was, well, if we send a probe and we scoop something up, we can never say there definitely isn't life, but we can say there is. Do we have any spacecraft that have that scooping up potential?
Yeah, well, you know, the imperative is there to investigate with spacecraft. Like you say, with remote observations, there'll always be some doubt. And there are several spacecraft being considered that could shed light on this. As far as actually scooping something up and bringing it back,
I'm not saying bring it back. I'm just saying scooping it up and looking at it.
Okay. Because some people now have been on the chatter online. People saying, "Well, we need to bring back a sample," and that's pretty hard to do.
That seems like a terrible idea.
Yeah, that's right. So I'm glad we clarified that. So we're not talking about, at least in the near term, bringing back a sample, but yes, going there and in place investigating with instruments, that's the thing to do. And there are a few spacecraft that, there are a couple Venus spacecraft actually now under active consideration by NASA in the Discovery program, one of which is an entry probe that would at least fall through that region and take measurements on the way through and on the way down and look at the gases and the clouds and try to understand more about what's going on. The next step would be to do something that's really dedicated to that cloud region and maybe try to actually suck in some cloud particles and, look at them with a microscope or something, see if there's anything in there, and maybe go with a balloon or a some kind of, solar powered glider and spend some time in the clouds and looking around. There are a number of really good ideas that are being at least considered and designed and batted about. And I think that, I think that there's been momentum building for new Venus missions anyways, because we haven't had enough. It's been, other than a couple, the European orbiter and the Japanese orbiter, which are both great missions, but they're sort of limited in what they can do. We haven't had missions that have actually gone into the atmosphere of Venus, down through the clouds, down to the surface in decades. And there's been momentum building for it anyways. And I think that this discovery, this announcement, will only add to that momentum. It's it's a really nearby planet with a lot of interesting questions, not just the possibility of life, but things to learn about the climate and about how Earth-like planets work in general. And so we have to go with new missions. And yes, this is a question that if it doesn't just go away because like, oops, we made a mistake, or oops, there's an obvious source, then how could we not want to go there and scoop some stuff up and really see what's going on in those cloud particles?
It's an amazing time to be alive. Unfortunately, with the time that it takes to build and launch a mission, we need to stay alive for probably another decade or so. But
that's right. Everybody, do your exercises and eat well and advocate for new missions.
It's what we're gonna do. It's what we're gonna do. This has been an amazing interview that has gone far too quickly. We didn't get to audience questions. I'm so sorry, everyone. Are you going to be talking about this at all during your Funky Science Story Hour this week?
Oh, I think it's going to be unavoidable.
Okay, so that will be tomorrow at 3 p.m. Eastern.
Thursday.
Thursday, yes, sorry.
3 p.m. Eastern, yeah.
Thursday at 3 p.m. Eastern. So tune in, everyone, to catch more. Now, where all can people learn about your work and track down that chapter that you're responsible for writing? Thanks for asking. So if you go to my website, which is funkyscience.net,
you can find a couple of things. Actually, I put up there recently. One is the chapter from Venus Revealed in 1997, where I floated, so to speak, this idea of life in the clouds on a post-Magellan Venus. And I also just put up there's a section of the website with some of my scientific publications, and I put up a review chapter that I wrote with a colleague a few years ago, sort of summarizing the case for astrobiology on Venus. So if you want a nerdier take, there's also a scientific chapter that you can find on there.
And you've also been doing a fair amount of tweeting of everything that's going on. And so folks can also find you as Dr. Funky Spoons, I believe.
That's right, Dr. Funky Spoon. If you can put up with my occasional political rants, you'll also find some good science and fun other stuff on there as well.
It's 2020. This is the year we all need to be political so that, well, our future can go just that much better.
Yeah, if things keep on this way, we're going to have to move to Venus.
Oh, good Lord. I saw someone made the comment earlier in this production that Venus might have a more breathable atmosphere than California right now.
It's a toss-up.
So if you had one thing that you wanted everyone to walk away from today as their go-to when someone asks them about Venus, what is the most important thing that people need to remember right now?
That it's a world of mystery right next door that we can and must go and explore.
And I think that need to go get data is really, that's where all science needs to start. You can't necessarily, or at least you shouldn't. You certainly can, but you shouldn't be off making hypotheses without actually looking up. So
Indeed.
This has been great. Thank you so much for joining us, David. And to all of you out there, thank you for being here. This has been the Daily Space. The two of us both work for the Planetary Science Institute, a 501c3 nonprofit that is out to explore our solar system and sometimes beyond. This show was written by me, and our web content will be produced by Beth Johnson. Our show will be engineered by Ali Pelfrey, and we are here thanks to the generous contributions of people like you. We are planning our yearly Hangout-a-thon for October 25th and 26th. Go find out more about what's going to be happening and how you can donate today to help us cover our 2021 physical year costs by going to CosmoQuest.org. We will see you over there. But for now, I would like to say one last thank you so much for being here, David. And to all of you out there, wherever you are in the world, have a fabulous morning, evening, or afternoon. And
Thanks,
go
Pamela.
forth and be awesome.
Always a pleasure.